On the Atwood's problem, we've gotten to the point, I think with you guys, we had actually gotten to the point where we had said, sorry, the background noise is my children running around the house. I think that you guys had said that this was probably B, the one with the least inertia. And so you guys said probably B, having the least inertia. So having the least inertia means that it would accelerate the fastest. I think that you probably meant the most inertia. This one's probably most, because it's going to go the slowest. But that's what we were talking about in class. Then the next question says, determine the acceleration for each system. Now this one seems pretty tricky, because what we know is that force is equal to mass times acceleration, and we don't have numbers for anything. We don't have numbers for force. We don't have numbers for mass. We just have big M, so we know that those two are an equal amount of mass, and those added together is 2 times that, but we're not told how many kilograms that is. But we're going to go ahead and take a stab at this. So this is determine acceleration. If I want to know acceleration, I know that I have to divide the force by the mass. So I at least know that much. The way that I'm going to write this in here is I'm just going to kind of imagine that these are columns. So we're going to do a system A, system B, and system C. So for system A, if I want to try to figure out acceleration and I'm looking at force, we know that force is equal to mass times acceleration. So I'm just going to write that. Mass times acceleration divided by the total mass of my system. And if I look at my system, my total mass is 2 times whatever that mass is. So I'm going to write 2m. Turns out that I can simplify this. I can make this equal to, these two are, they cancel each other out, that I have a over 2. Sorry, I'm going to do this so it looks nice. A over 2, which looks a lot like 1/2 times A. And we know that the A that would be relevant for this problem is going to actually be acceleration due to gravity, which the number that we used for that is minus 10 meters per second squared. So 1/2 times minus 10 is going to give us a value of minus 5 meters per second squared. Sorry, I'm listening to my people downstairs. So we can actually get a value for our acceleration there, even though we don't have a value for mass, because it cancels out. So for system B, we're going to do the same thing. Acceleration is equal to our force. And again, our force here is mass times acceleration due to gravity, because these guys have identical forces pulling on the masses that are sitting on the table. So this is going to be mass times acceleration due to gravity divided by the total mass of our system. Now, unlike the first one, this one's got 3 blocks, 1, 2, 3. So I'm going to write 3m down here. The m's cancel, and what we are left with is acceleration due to gravity divided by 3, which is going to give us minus 3.33 meters per second squared. So it turns out that, in fact, B has less acceleration than A. And you guys, I think, predicted that the other day. Sorry, my camera's lagging. You guys predicted that the other day, because if we compare these two, they have the same amount of force, but system B has to pull on more mass. And so that means it's going to accelerate more slowly than system A does. And that's, in fact, what the numbers indicate. System C is a little bit different. It has the same mass as system A, except we have more mass hanging up, which implies that we're going to have more force. So our acceleration here is going to be 2 times mass times acceleration due to gravity. G is another way that you can write acceleration due to gravity. We just don't usually use that in class. Divided by our total mass, and our total mass here is going to be 1, 2, 3m. M's cancel, and so our acceleration here is going to be 2/3 times acceleration due to gravity, which is going to be about minus 6.66 meters per second squared. So again, this is a vector, so our negative sign only tells us that we're being pulled in the direction of that downward force. And the one with the greatest acceleration is C, the lowest is B. If we look again at our Atwood machine diagrams up here, we can predict that that's what would happen. if we've got one mass sitting on the table, we're going to have more acceleration where we have two masses contributing to the force. If we've got a total set of three masses, like we do with B and C, if we have two contributing to the pull force downward compared to one, we're going to have a greater acceleration than with system B. So hopefully that kind of clears up a strategy for being able to solve that problem. If anybody has any questions, make sure you unmute yourself so that we can talk about that. If I don't hear anybody interrupting us, though, we're going to go on and talk about problem number 8. Problem number 8 probably looks pretty similar because we've been doing problems like this in the previous unit where we were looking at balanced forces that were not, that were in a tilted plane. So here we've got a child that's going down a slide. Slides are great. Today it might have been more appropriate to have sleds, but here we are. So what I'm going to do first is set up my axis so that I'm looking at the axis that my problem is happening in and use that to solve problems. I know that I'm going to have forces that are parallel to the surface and perpendicular to it. So that's going to be the way that I kind of start this. So I'm going to draw an axis that's roughly parallel to my hill and perpendicular to it. There we go. And then I'm going to go ahead and start putting my forces in. This is quantitative force diagram, so it wants me to solve things with numbers when I can. So first I'm going to draw gravity. That's my favorite one to draw first. I also can make that quantitative because I know the mass of the child. So a 30 kilogram child is going to have a force due to gravity of 300 newtons. And because it's downward, I'm going to go ahead and make that negative. So that's going to be my negative side. I usually like to make up positive, that's negative. And these signs, this is going to be forward, so I'm going to make that positive, and backwards would be negative. Keep in mind that when you're doing things with signs, it may actually be more helpful for you guys to draw them on your diagram and use that to determine your values, because the fact of the matter is if you're relying on trig to do that, you need to start with 0 being this line, right? So this would not be this angle, it would be the entire thing. And so just be aware of that as you're working on these problems. So the other forces I need to be aware of, I know that I'm going to have normal force, right? That's going to be perpendicular to my hill. I'm also going to have friction backwards, and I'm told that that value is 160 newtons, but because I decided that's the negative direction, I'm going to make it minus 160 newtons. Okay, so I'm going to wait to put other things in there until I see what happens with the rest of the problem, even though this is quantitative, so we'll come back and do those. So for part B, it says, write the equation for the forces on the child parallel to the slide. So that's going to be this line, and find the net force on the child. So this looks a lot like I need a net force equation. So I'm going to write F net is equal to my total mass, the mass of the child, times acceleration. And this is not acceleration due to gravity. This is acceleration of an object. So I'm not going to write a G there. And that's going to be equal to friction plus my force due to gravity that is parallel to the slide. So when we draw that, remember, if we have a force that's not on our axis, we have to break it into components that are on the axis. And we're going to do that by drawing a rectangle and then projecting them. So here's my rectangle. And then my components are going to be along the sides that are on the axis. So this is my force due to gravity that's in the vertical axis. This other one is force due to gravity in the horizontal axis, or parallel to my surface. So those are going to be the two that I can solve for to figure out what's going on with the other ones. Here it says find the net force. I don't know FGX yet, so the way I'm going to solve that is by looking at my net force, my mass, my acceleration. Can I do that? I can't do that yet. So it looks like what I'm going to have to do is solve for FGX to be able to get at my net force. In order to do that, I'm going to have to figure out what that angle is there. So we're given an angle of 55 degrees, and that angle is the angle between FGX and a horizontal line. So I'm going to try to write that in there carefully. So that's 55 degrees, which means that if this is a right angle, then this angle up here is going to be 35 degrees. Sorry, I kind of wedged it in there. So my triangle, again, I'm going to have gravity, G, and that has a value of minus 300 newtons. And then I have FGX, my horizontal component of gravity, which is what I'm trying to find. And I've got an angle of 35 degrees in that triangle. To solve for FGX, what I'm looking at here is the relationship between an adjacent leg and the hypotenuse for a 35-degree angle in a right triangle. So I'm gonna have to look at cosine of 35 degrees. It's gonna be equal to FGX divided by minus 300 newtons, the hypotenuse. So FGX is gonna be equal to minus 300 newtons times cosine of 35, which is going to give me a total force of 271 newtons. So if I come down to part B, I'm just going to write this on here, 271. I want that to be positive because of the direction that it's going. So I actually know both of these now, so I can solve for that. So this is going to be equal to minus 160 newtons plus 271 newtons. So my total net force is going to be 111 newtons, and that's going to be the difference between those two. Since I have a quantitative force diagram up here, I also want to solve for FGY. So now I have some little space here that I know is extra. I'm going to go ahead and do that. If that's 35, might as well keep my colors. This is going to be a 55-degree angle. And so I can use the cosine of 55 to figure out that. So the cosine of 55 degrees is equal to FGY divided by 300 newtons, minus 300 newtons. So FGY is equal to minus 300 times cosine of 55. So that's going to be equal to, just 1 second, 300 times, where'd my cosine button go? All right, so, oh, really? That's tiny. I got 6.6 newtons. That's very small. That seems impossibly small. Yep, that's what I got. Okay. We're just going to roll with it. So we've got 6.6 newtons. It's just so tiny. I feel like it should be closer to 200 something. I wonder if my calculator's got like... It's in radians, guys. I'm going to fix all the things down. Probably means my other answer is wrong too. Okay, so my calculator is in radians, because the problem that I was having is that if I add that and that, I have less than 300. And that's not how triangles work. So it turns out I was using radians. This should be 245 newtons. This guy should be 172 newtons. That's much better. I feel better about that. So if that's the case, this won't be that. That'll be 245 newtons. This will be 85. Okay, sorry about that. That's a big mistake. Yikes. I don't know why my calculator is in radians. I never use radians. All right, so then the last thing we need to do here is calculate 172, is calculate the child's acceleration. So if we know what our net force is, then we can use Newton's second law to figure this out. So F net equals mass times acceleration. We're trying to solve for acceleration. So acceleration is equal to F net divided by mass. Our net force is 85 newtons. The mass of our child is 30 kilograms, which means that our child is accelerating at 2.8 meters per second squared. Hopefully they don't accelerate at that rate forever, or the slide is a little bit short so that they don't end up hurting themselves. Do you guys have any questions about number 8? I apologize again for this mistake with the radians thing. That's a little bit nuts. Okay, so we're going to start looking at worksheet number 2, where we're going to practice using Newton's second law to solve problems. Remember, Newton's second law is force equals mass times acceleration. And now that we're in a situation where we're looking at problems that are unbalanced, we can expect that we have acceleration that is not 0. Basically, in the last unit, we were always assuming that the acceleration was 0, and so those forces were balanced. But now that's no longer true. So in this first problem, we've got a 4,600 gram helicopter. I'm going to go ahead and write that down. That's a mass, so 4,600 kilograms, and the helicopter is accelerating upward with 2.0 meters per second squared of acceleration. So again, this is an unbalanced situation. The forces in the two directions are not equal to each other, and that's why we have an acceleration. We're asked to determine the lift force exerted on the propellers by the air. We're going to make a quantitative force diagram, write a net force equation. All right, so in order to do that, yeah, so this quantitative part is going to tell us that we need to solve some things. So first, we need to draw a force diagram. That's where we should always start these problems. So I'm going to draw a dot to represent my helicopter. I've got an arrow that represents lift. So there's lift. And we know that upward, that force is going to be greater than the downward force due to gravity, because our helicopter is accelerating upward. We know that gravity, the force due to gravity, is equal to mass times acceleration due to gravity. Here our mass is 4,600 kilograms, and our acceleration is minus 10 meters per second squared. So our force due to gravity is going to be minus 46,000 newtons. So we can solve for that. Next, we need to write a net force equation. So our net force is equal to our mass times our acceleration, and that's equal to our lift plus gravity. We know gravity, we know mass, we know acceleration, so we can solve for lift with this, and that will let us finish our quantitative force diagram. So we're going to focus on this, solve for lift. Let's see. I'm going to rearrange some of these things. I'm just going to subtract force due to gravity from the other side. So lift equals mass times acceleration minus gravity. So our mass is 4,600. That looks terrible. Sorry, our mass is 4,600 kilograms. Our acceleration is in the positive direction, 2 meters per second squared. I'm going to subtract from that our minus 46,000 newtons. So this first value, 2 times 4,600, is going to be 9,200 newtons plus 46,000 newtons. So our total lift is going to be 55,200 newtons. So one thing that you could notice from this is that our net force doesn't actually show up as an actual number on our force diagram. Our net force turns out to be, the net force was this 9,200 newtons. Our net force is actually the difference in magnitude between these two. So it's kind of interesting to think about. What I want you guys to do with the rest of the class period that we have today is to finish problem number 2. So for problem number 2, what I would recommend is that you draw a force diagram versus make a quantitative force diagram. Draw a force diagram for the groceries, and then to figure out the problem about, do the groceries stay in the bag, look at how much force the bag has to put on the groceries to keep them up. And keep in mind that the limit on that has to be 250 newtons. If it's above that, the bag cannot withstand that, and the groceries will accelerate downward. So that's kind of the way to think about this problem. All right, so I'm going to go ahead and turn off the screen sharing. We have How much time do we have left? We have about 6 minutes left. Is that right? So if you guys have any questions, you can feel free to ask me. I just want you guys to finish this before tomorrow, whether that's an in-person day or an at-school day.